Hello, my name is Kieran Mastel, and today I'll be talking about two-prover perfect zero knowledge for MIP star, which is joint work with my supervisor, William Slofstra. First, I'll talk about multi-prover interactive proofs. The intuition here is that two computationally unbounded provers, Alice and Bob, want to prove that a string X is in a language L to a polynomial time verifier. The players, Alice and Bob, can strategize together before the game begins, but they're not allowed to communicate with one another during the game. We call an MIP protocol a sequence of games that's indexed by strings X, such that if X is in the language, then there's a strategy that the players can employ such that they win with certainty. But if X is not in the language, then no matter which strategy the players employ, they can only win with probability at most S, which we call the soundness parameter. An example of such a scenario is the graph coloring game, where Alice and Bob want to convince the verifier that they know a 3 coloring of a graph G. Here, the questions I and J are vertices, and the answers A and B are colors. If Alice and Bob receive the same vertex, they must respond with the same color to win, and if they receive adjacent vertices, they must respond with different colors. Alice and Bob only have a perfect strategy here if the graph is actually 3-colorable. We denote by MIP the set of languages with a multi-prover interactive proof system where the provers have classical resources, such as shared randomness. In quantum mechanics, there's now the possibility that Alice and Bob can share some entanglement. Here, Alice and Bob share a quantum state in a tensor product Hilbert space, and upon receiving her question I, Alice performs a positive operator valued measure to get her answer A. Similarly, Bob conditions his answer on a POVM. The probability that the players answer AB on question pair IJ, then, is just given by the expectation value of the tensor product of their POVMs. We call the collection of measurement operators and the state a strategy for the players. So that's the freedom that they have in determining how they're going to respond to any given question pair. An example of how this allows the players more power than merely classical resources is that there are graphs with no 3-coloring, but for which the provers can play the 3-coloring game perfectly if they share entanglement. We denote by MIP star the class of languages with a multi-prover interactive proof system where the provers can use entanglement. Now let's talk about perfect zero knowledge. The intuition here is that Alice and Bob want to prove that X is in the language without revealing any other information. What we mean by this is illustrated by this picture. When the verifier interacts with Alice and Bob in an MIP star scenario, all that they see is the probability distribution PABIJ generated by the players answering AB to question pairs IJ. We say that this interaction is perfect zero knowledge if there is a polynomial time Turing machine S, called the simulator, that can output a correlation PABIJ from inputs AB and IJ, such that if X is indeed in the language, this correlation corresponds to a winning strategy for the players. The verifier doesn't learn anything in this scenario because, since computing the winning correlation is a polynomial time computation, and the verifier is a polynomial time Turing machine, interacting with the players does not show the verifier any information other than the fact that the players can generate the correlation PABIJ that the verifier already expected to see. Perfect zero knowledge for MIP and MIP star has been the subject of a lot of great work. It was already known at the introduction of the complexity class MIP that all languages in the class admit perfect zero knowledge proof systems. In 1990, Babai, Fortnow, and Lund famously showed that MIP is equal to NEXP, and that 2 provers and 1 round of interaction are enough to capture the whole complexity class. After the introduction of MIP star, Chiesa, Forbes, Gurr, and Spooner showed in 2018 that NEXP is contained in perfect zero knowledge MIP star with 2 provers and polynomially many rounds of interaction. So perfect zero knowledge proofs with entanglement are at least as powerful as classical multi-prover interactive proofs. Then in 2019, Grillo, Slofstra, and Ewan showed that MIP star is contained in perfect zero knowledge MIP star with 4 provers and 1 round of interaction using a technique called simulatable codes. Then stunningly, G, Natarajan, Vidic, Wright, and Ewan showed in 2020 that MIP star is equal to RE, the class of recursively enumerable languages, and that 2 provers and 1 round are enough to capture the whole complexity class. This prompts the natural question: can we bring perfect zero-knowledge MIP star down to 2 provers? In this work, we answer this question in the affirmative. That is, our main result is that MIP star is equal to perfect zero-knowledge MIP star with 2 provers and 1 round of interaction. One way you might think to try and go about proving this statement is by improving the techniques of Grillo, Slofstra, and Ewan using simulatable codes. The data is hidden from the verifier in a simulatable code argument by splitting a quantum state encoded in a quantum error correcting code amongst the 4 provers. If we reduce the number of provers, we can no longer split the encoded state into as many pieces, and so the data hiding argument falls apart. The technique we do use is employing the MIP star equals RE theorem to bring us down to a 2-prover 1-round protocol, and then showing that we can reduce this 2-prover 1-round protocol to a perfect zero-knowledge protocol with the same number of provers and rounds. To prove our reduction, we specialize to a type of interaction called a Boolean constraint system game. In a BCS game, the questions I and j are indices of constraints in a Boolean constraint satisfaction problem. The players then answer with satisfying assignments phi a and phi b to the constraints that they've been asked for. The players win if their satisfying assignments agree on the variables they share. An advantage of Boolean constraint system games is that we can work with assignments to the variables rather than with arbitrary strategies. In addition, BCS games allow for the use of Killian randomizing tableau, which let the players demonstrate to the verifier that they hold a satisfying assignment to the original BCS without revealing the value of too many of their assignments to the original variables. The first row of the Killian randomizing tableau, denoted by pi1 up to pi d, is called a permutation branching program, which is a way of generating permutation-valued variables, pi1 up to pi d. Here, they're variables in S5, from the assignment to the original variables in the Boolean constraint. The permutation-valued variables are generated in such a way that their product will be equal to sigma, some 5 cycle, if the assignment to the original variables satisfies the constraint C, and if the assignment to the original variables does not satisfy the original constraint, the product of these permutation-valued variables will be equal to the identity. Each subsequent row of the tableau is generated from the previous row by multiplying on the left and right by uniformly randomly selected elements of S5. These elements are multiplied in such a way that each row of the tableau looks uniformly random relative to the previous row, but the product of all the elements of each row are the same. In particular, the product of all the elements on the 4th row will be equal to sigma if the original assignment to the original variables satisfies the original BCS constraint, and will be equal to the identity otherwise. By limiting the verifier to checking that the product of the 4th row is equal to sigma, and that individual elements tp plus 1q have been constructed correctly from TPQ, the element of the previous row of the tableau directly above it, we can prevent the verifier from learning high moments of the assignments to the original variables that the players hold. And typically, before performing a Killian randomizing tableau reduction, we ensure that the low moments of the player's assignments to the original variables are uniformly distributed, and so can be simulated by the verifier. Dwork, Feige, Killian, Knorr, and Safra use permutation branching programs and Killian randomizing tableau to prove that there's a 2-prover, 1-round perfect zero-knowledge proof system for 3-SAT. In order to use randomizing tableau, the permutation branching program on the first row blows up the length of the circuit exponentially, so we need constant clause size in the original Boolean constraint system to recover constant size tableaus. This is why Dwork, Feige, Killian, Knorr, and Safra talk about 3-SAT. It's a result of the MIP star equals RE theorem that Boolean constraint system games are universal for MIP star. This can be seen by employing iracularization. We show that perfect zero-knowledge MIP star with 2 provers and 1 round of interaction is equal to MIP star by showing quantum soundness of the randomizing tableau transformation. We prove the quantum soundness of these classical transformations by identifying 2 types of transformations between BCS games that appear implicitly in a lot of previous work, and introducing a formal framework for thinking about these transformations. The first and easier type of transformation is something we call a classical homomorphism, which is a constraint-wise map of BCS to BCS in a way that maps satisfying assignments to satisfying assignments, and assignments that disagree on overlapping variables to assignments that disagree on overlapping variables. There are many instances of this in the literature, notably the locally commutative reductions of G, and these transformations preserve quantum soundness right out of the box. The second and more difficult of the transformations we identify is called a subdivision. In a subdivision, we take what was one constraint in the original BCS and split it up into multiple constraints in the new BCS. A key point that makes the analysis of these things difficult is that we can no longer rely on observables for variables in different contexts in the target of a subdivision to commute with one another. For example, the observables for x1 and x5 in the original constraint C here will commute with one another because they appear in a constraint together. However, the observables for x1 in the constraint D1 and x5 in the constraint D2 are no longer required to commute with one another in this new constraint system that we generate via subdivision. This difficulty can be overcome, and we prove that if B prime is a subdivision of a BCSB with a strategy who has winning probability 1 minus epsilon, then there's a strategy S prime for the game corresponding to the original BCS with winning probability no greater than 1 minus polynomial times epsilon. And so a polynomial amount of parallel repetition allows us to recover a constant completeness soundness gap after subdivision. In order to prove theorems about the soundness of BCS reductions like the one on the previous slide, we introduce a formalism we call weighted algebras, where A is an algebra of observables and mu is a finitely supported weight on the algebra. We use the weight to introduce a quantity which we call the defect that measures how far strategies are from being perfect. By looking at how transformations such as context splitting and classical homomorphisms affect the defect, we can analyze how they affect the soundness of BCS protocols. An advantage of the weighted algebra formalism is that it works for different types of quantum strategies. For example, for commuting operator strategies, we can prove this theorem that perfect zero-knowledge BCS MIP-CO, that is MIP with commuting operator entanglement, with 2 provers and 1 round of interaction, is equal to BCS MIP-CO with 2 provers and 1 round of interaction. And if we were able to prove the same theorems about MIP-CO that we know about MIP star, for instance, if we were able to show that BCS MIP-CO 2-1 was complete for MIP-CO, then we would have a similar perfect zero-knowledge 2-prover 1-round result in this context as well. And we expect that the weighted algebra formalism for reductions between BCS games will be useful in other contexts as well. Thank you very much for listening.